So PLS is a polynomial local search. So it's a class of a general problem of finding a maximum, a global maximum, when you look only locally. And the question is how efficiently you can do that. So that's something which is not actually, from what I know, known exactly how it can be done, but it seems to be hard, and that's the complexity class. So finding pure Nash equilibrium in general is hard, because you need to check all the possible strategy profiles, and of course there are, so say there are S1 strategies of player 1 times S2, say, let's use the notation so that it's going to be not only the set but also the number of strategies, player 2 and so on. So it's exponential in the number of players, and therefore just brute force is not something polynomial, but maybe there is some option to do it polynomial. Anyway, that's PLS complete. So it's at least as hard as any problem in this polynomial local search group. And finding mixed Nash equilibrium, when we formulate, it can be formulated in the sense that finding the support of this mixed Nash equilibrium, so only the strategies which are played with non-zero probability, because if that's found, we already can find from that in the polynomial time, and I think by solving a certain linear program, the equilibrium itself. So that amounts to a combinatorial problem, what I want to say, and this finding is also known to be hard. It's PPAD complete. Now PPAD is a polynomial parity arguments on directed graph. So you have a directed graph and you have a problem there to solve. It's not very simple even to define, but it's a class of problems which also is not known to be hard, not known to be simple, is assumed to be hard, and finding a mixed Nash equilibrium is at least as hard as any problem in that class. So those two are hard, and on the other hand, at least approximately finding a correlated and definitely coarse correlated Nash equilibria is polynomial. Now, as I write here that pure Nash equilibrium and mixed Nash equilibria are hard, but in some specific classes of games, like two-player zero-sum games, that's actually possible to find in polynomial time, but in general these are hard. But as I said, that when we look on a broader, generally speaking, solution, which is correlated equilibria, then we can find it. And moreover, there is a natural dynamics of learning, so that players learn in a certain way, and that converges to such an equilibrium, and that means that we can assume that we can expect actual markets, actual interactions to converge to that equilibrium. So these are definitely important notions. So now we're going to just touch upon this correlated equilibrium, and we start with an example. So consider this famous example of battle of sexes, so that you have male and female, or does not matter actually in this form. So two people, one likes football, another one likes tennis. So they want to go to something together. So if they don't go together, they both get the profit of 0. They both get the profit of 0. But if they go together, then if they go to football, then the guy who likes football gets 2, and the girl who likes tennis gets 1. While if they go to tennis, then the situation is opposite. So the football lover gets 1, and the tennis admirer gets 2. Now, there are two Nash equilibria, two pure equilibria, when they go both to football or when they both go to tennis. And the problem is that each one of them prefers one of the players. They're not symmetric, they're not fair, despite that the game is symmetric. Now, there is also a unique mixed Nash equilibrium, which is symmetric, that then there's a certain positive probability, because the randomization in the mixed equilibrium, they are independent, the randomizations of the players, that can be that they actually are not matched. So they, with a certain positive probability, can both get 0. And the average utility is therefore less than 3. So the sum, the social welfare, the total social welfare is less than when they both play, let's say, deterministically, football or tennis. It's indeed symmetric, it's fair, but they will lose in social welfare. Now, what if we randomize in an interdependent manner? So what that someone tosses a coin, and if it's someone trusted, and if it's let's say you have a fair coin, so it can be either faces or tails, heads or tails. So it's if the coin falls heads, then that trusted mediator, or it can be simply that the coin is publicly known, then they both play football. If the coin falls tails, then they play tennis, or it even fits the letters, so face and tails. But I meant, of course, football and tennis. So basically, in this case, they randomize in a dependent manner. They either both play face or both play tennis. The expected social welfare here is 3, and it's still symmetric and fair. So you see, and now it's still an equilibrium. We're going to formalize what it means, but here it's an equilibrium, at least informally, that in the sense that given that the other player follows that, it's always optimum for me to follow that, because if I know that I'm told, let's say I'm the man, so I like football, player 1, I'm told, today play football. I know the other guy, goal in this case, so the other player follows that. Definitely it's better for me to play football, because otherwise I will get 0. Even if the decision is to play tennis, which I don't like, it's better for me to do it, because I know that the other person will play tennis, so if I don't want to get 0, I will play tennis. So it's always profitable for me, it's the best response for me to follow that strategy if the other person follows the strategy. And that's more realistic, because at least the option to model this interrelation is more realistic than when we may not model, because it's possible that players indeed, people in a normal relationship, it's possible that they will randomize in a dependent manner. One day we do that, another day we do that, or maybe we play somehow randomly. Why randomize independently and lose sometimes because of going to different places when we can randomize dependently? So it's fair, it avoids zeros, it avoids those and those outcomes. So in general, any player should be able to optimize for any signal. Maybe the signals are not the same like here, but for any signal, given the strategy of the others, a player should be able to optimize. And formally, let us define what we mean by correlated equilibrium. Here we follow, by the way, the book by Osborne and Rubinstein. So in this lecture, we follow Osborne and Rubinstein in everything besides strong equilibria, which I think they don't cover. But in strong equilibria, we really look at the basics. So that's something we don't need to follow a book. but in the area of correlated equilibria and in the area of evolutionary stable strategy, we follow Osborne and Rubinstein. So if you want, you can read that too. In the lecture, I tried to kind of masticate the material, so to speak, that it will be even simpler for you to understand. Because it's actually simple material. It's simply very technically confusing. But it's simple. But I tried to make it indeed simple. That's what I've tried to make, so that you do gain from listening to the lectures in comparison to just reading the book. But you're welcome to read the book. It's quite, I think that Osborne and Rubinstein is quite a good book. At least in these chapters. That's why I'm using them. So the players should be modeled that they randomize using some correlation signal. It can be in particular that they don't have correlation. It can be that it's a mixed strategy. It can be that it's in general and the general strategy that it's a pure Nash equilibrium. But in general, there is somehow correlated signal. So that there is that actually each one has its own signal and they are correlated. Thereby the signal correlates them. Formally, given a game, a correlated equilibrium consists of a following probabilistic structure. That's a part of the equilibrium. Please note, it's an intrinsic part, an endogenous part of the equilibrium. It's not a given with the game, but an equilibrium contains, like the mixed strategy equilibrium contains the probabilities. So let's say that I randomize with probability half I do that, with probability 1/3 I do that, with probability 2/5 I do something else. Excuse me, half, 1/3, and 1/6. Yes. Anyway, so I'm just confusing with numbers. So 1/6, 1/3, and half. Let's say that's how I randomize. These probabilities are part of my strategy, are part of the equilibrium in the case of mixed strategy. In a similar manner, in a correct equilibrium, the probabilistic structure I'm going to now describe is a part of the equilibrium. That's important. It's not given with the game. So a correlated equilibrium consists of the following probability structure. The probability space, which is a finite probability space. So there is a function simply which gives a probability for any element of this space, the probability function. It's finite, so every element has a probability. The sigma algebra contains all the subsets, if you want to be formal in the language of probability, of the theory of probability. So a finite probability space, and the probability measure ascribes a probability to every element. And now each player has an information partition of this probability space. So the information partition says what can I know. So player I knows only distinguish between states in different information partitions. There are two states in the same information partition, but player cannot distinguish and cannot behave differently in those two states. So, of course, you can think of the information partitions being like extremely fine for everyone, so that the partition consists of the singletons of all the elements, but in general does not have to be so. Each player has some own information partition, and the strategy of a player is a function from the information partition to the SI in the game. So here the SI of the game, they should be called actually actions, not strategies, because the strategy is not SI, but it's the SI which is assigned. It's the rule which assigns an action to a certain outcome of the probability space, such that if there is a partition, the two outcomes belong to that partition, then the rule has to assign those outcomes to the same action. So the rule is constant on the partition element. In other words, this rule can be seen as a function which goes from the partition to the probability space. So it only knows in which partition I am. It only knows, say, that the elements are countries, and I behave differently in different countries. But the actual information partition is only which language is spoken in those countries, assuming that there is one language in each country. So then I behave depending on the language. So if, let's say, the language is German, I behave in the same way. It can be Germany, it can be Austria, but I behave in the same way because I only know the language. Another person may have another information partition which says which continent the country belongs to. And then the person behaves in the same way, whether it's the USA or Canada, but differently when it's USA or let's say England. Despite that both or Britain, despite that both have the same language. But the person who looks at the language actually will behave differently when it's USA or Britain because they have different continents. Excuse me, the person who looks at the continent will behave differently when it's USA and Britain because they belong to different continents, but it will behave similarly when it's USA and Canada. The person, on the other hand, who looks at the language will behave differently when it's Germany and who looks at the language will behave differently if it's Germany or England, but they will behave similarly if it's a continent because they are both in the same continent. Okay, so then we've defined what a strategy means. So only in this case, actually, a strategy means something else from what we usually mean. A strategy is a function from this probability space, so from this sample space. I would say probability space is all the tuple, so the sample space to the set aside. And given this probabilistic structure, we require stability. What does it mean? It means that for every player, the strategy of the player is optimum given the other players do what they do. So for every player, ice, it's not I prime, it's just ice. It's a possessive form. Strategy, S prime, any other strategy of that player I, here it's a prime actually, so S prime, any other strategy of that player, and again, spin strategy means that if there exists an element where two elements of omega belong, then S primes are equal in both elements. So a strategy strategy of a player only looks at the element of the probability of the partition of that player. And the expectation of the strategy of the player is the best possible given that the others behave however they behave. So formally, the expected value, and we'll go over all the elements in omega and we look at what is the probability of the element times what the player gets when every player plays hers I on that element, is at least as good for that player. That probability is at least, that expectation, so sum of probability is times utilities, or in other way, utilities weighted with the probabilities, or another way, the convex combination of utilities with the probabilities as coefficients is at least as good for the player as the combination of the expected value for that player with the same common probability function PR when the rest of the players use the same strategy, but that player goes to some other strategy as prime. So they have a possible any possible unilateral deviation will not improve that player's utility in expectation. Now two remarks. One, as I already said that this probability space and the partitions are an intrinsic part of this correlated equilibrium. So we can speak of another equilibrium if we change this. And we assume that unlike the knowledge, unlike the information partition, which can differ in general per player, we assume that the PR for probability function is common. And it does matter. So if we allow that function to be dependent, so one player believes something different from the other player, then you would have a broader set of possible, a strictly broad, in general, set of possible correlated equilibria. We don't study that. But there is a possibility to assume that and to see that it is going to be harder. Excuse me, is going to be the possibility is going to be general, more general, but we don't study it. So we have a probability space, and given the space, the strategy of play I is optimal given that the other players play what they do, and an immediate observation. It's observation, but it's not so trivial to prove. It's kind of intuitive that given a game, this tuple of omega probability partitions and strategies, remember strategies in the sense of functions, is a correlated equilibrium if and only for each element of omega which has a positive probability, so only for those, of course, it's important, the conditional expectation of the utility of player I is at least as good as what would happen if player I deviated for any deviation. And the condition is that we are in the partition of this element. Well, if it's well defined, because if the probability of the element is positive, then the partition, so as a set of elements, has a positive probability, so this conditional expectation is well defined. So basically, the definition says that a profile is a correlational equilibrium. Excuse me, a profile is, yes, a correlated equilibrium, correlated. If the expected value of a strategy is the best possible, given that the others play the same strategy. So there is no sense to deviate from it unilaterally to another strategy. So the same as in all the others, I mean in mesh equilibrium and in mixed equilibrium, simply that here the randomization is allowed to depend on something. And that the observation is that, okay, it's the same, we claim, as saying that the expectation, knowing that we already have landed in a certain player knows that we are in his PI information set. So from his point of view, so the stylized PI is the set of those sets. It's a partition, and each set is normal capital letter. So it's normal capital letter. So knowing that we have landed in PI, it's better for me to play SI than anything else, given that the other players play whatever they play. So can even say that just the expectation is higher, or knowing whatever happens, it's better for me to play something. Okay, so why? Formally, well, intuitively it's clear. Because my strategy depends exactly on my partition element, and saying that the strategy is optimum, and expectation means for every partition element I do the optimum I can, given that what I know. And that's exactly what we say here. The conditional expectation is optimum. Now formally, well, first we say, as I've already mentioned, that the probability of element, by the way, okay, the probability of an element is positive. Strictly positive implies that the probability of the whole partition which includes the element is strictly positive, so the conditionals are well defined. And then, now one thing about the notation. Probability formally is assigned to a set. It can be a singleton, it can be an empty set. Well, when it's an empty set, it's 0. But so the set can be single, but it's a set. So we have used notation when we write probability of an element. It should be the singleton which includes S. Please note, it's I think it's an abuse of notation. I think also I'm not the only person who does this, but it's an abuse of notation. Please note that. Probabilities is in general a function from the set of subsets of all the subsets in the sigma algebra. In our case, the sigma algebra is all the subsets, but it's all the subsets. Okay, so I hope I will not confuse you. You are welcome to stay with an intuitive understanding of probability. I think it's going to be enough. So now let us prove the observation. The conditional expectation of utility conditioned by the partition element is, by definition of conditional expectation, going of all the elements on the partition element. What is the utility? Times the probability of that element, defined by the probability that we land in this partition element. So we just normalize everything by the probability of this PIC. And since the so I had a confusion in notation, so let me just go over the formulation of this observation once more to fix the conclusion. So given a game, the tuple probability probability sample space, probability space when it's a sample space, and the probability function, the PI is the player's information partition, and the strategies, in the sense the functions from the samples, from the sample space omega to the actual actions in S. All this is a correlated equilibrium according to definition. If and only if for any sample in this omega with a positive probability, and I said it's a shorthand to say that the probability is not, of course, of the sample, but of the singleton which contains the sample. For any such a sample, the expected utility of this player for playing Si when the other plays minus I, given that the player is in PI of S, so the player knows that she's somewhere in this PI of S, in this information partition is referring to S, is at least as good as the expected utility of the player for any other strategy as prime when the others play as minus I, given that all these conditions on the player being in this information partition of S. And that's for any possible deviation as prime. That's the idea. So that's how I should just write this conditional expectations. And now the proof is as follows. So first of all, we just notice the following. We make the following observation that the expected utility, what we basically have here, expected utility of the utility of player I, given that player I is somewhere in the partition of S, is by definition of expected utility. Now, as I said, and that holds that that's true that the S is S, since S has a positive probability, it means that the probability of the whole partition is also positive because it is at least as large as S. The probability is, of course, monotonous. So this conditional expectation is well defined. Now, the definition of conditional expectation is that the sum of all the D's in this PI, we go over all the conditional probability of D, so the probability of D over the probability of all this information set of to which S belongs, and then since we know that for any D in this PI, Si is going to give the same thing in Si, sigma is going to give the same thing in Si. By the definition of strategy, we said that here, that for any two elements which belong to the same information partition set, the sigmas are the same. That's what it means to be a strategy here, because player only knows that it's somewhere in PIC, does not know the exact value there. So for anything there, that's going to be the same. Si is going to give the same value. So we are able to take Ui out of this sum. So I just take it out of the sum, and then the sum simply goes for all the elements of the PIC and sums of the conditional probabilities conditioned on that they are in PIC. So that's simply 1, and therefore we just have this. So this expected probability of what player gets, the player knows that it's somewhere in PIC, is the value of the player in sigma IC, sigma minus IC, whenever one plays equal to C. Therefore, now we prove the first direction. So we need to prove that the definition is equivalent to this inequality for of conditional expectations. Now, first of all, we assume that we have this inequality of conditional expectations, and we prove our definition. So we said the inequality of conditional expectations knowing this transformation, that each one of the conditional expectations is equal to this utility, implies basically the inequality of the utilities. And therefore, by summing and multiplying by probabilities, we get the inequality of this probability weighted sum, and we get our definition of being a correlated equilibrium. That's true for any sigma prime, for any possible deviation, and so on. So, having this option to transform the expected conditional expectations, we prove that the equality of conditional expectations implies our definition. Now the other direction, in the proof of equivalence, knowing that's what we have proven, that's the transformation we have. The other direction is that assume that actually the inequality of conditional expectations does not hold. So there exists some C in PIC, which is a positive probability, such that the conditional expectations fulfill the opposite. So there is a strict inequality that plane sigma I is strictly yet another typo. My apologies. Let me fix the typo. Okay. So assuming there is some C with a positive probability such that the plane, knowing that we are in PIC, for I plane sigma I is strictly worse than plane some sigma I prime. And of course it's not for any sigma I prime, but there exists sigma I prime such that I've just copy pasted that here, and that's wrong. So now I need to. So there exists some sigma I prime such that plane sigma is strictly worse than plane sigma I prime, conditioned on PIC. So I assume that this other definition does not hold. Strictly, we have a strictly smaller than inequality. Then, by taking sigma 2 primes to be sigma prime for this PIC, and for any other case it's going to be just sigma, so it is going to basically incorporate the deviation for this PIC, for this element of S partition where I know that it's better to deviate, and for the other elements I thus just place the same sigma. So then, for elements in this PIC, I is going to strictly lose from plane sigma relatively to sigma 2 primes, and for other elements it's going to be the same. So we are going to have a strict inequality. Also, in our definition, remember that we multiply things by PRC, which is positive for C, for our C. So exactly when we have this strict inequality, we have a positive multiplier, so this strict inequality remains. And that's exactly what we may not have in our definition. So that we have found sigma 2 primes I that violates our definition. So we have proven that if we have this inequality for conditional expectations, then we have our definition. That was before in the previous slide. And in this slide, we prove that if we don't have this inequality of conditional expectations, then our definition is also valid. So we have proven now formally that our definition is equivalent to the inequality of conditional expectations. So being a correlated equilibrium is the same as saying that knowing where I am, it's always better to play what I have. So that's the intuitive thing. And then the next thing we prove that this correlated expectation, a correlated equilibrium, indeed extends a mixed Nash equilibrium. Because the intuition is that a correlated expectation, the same as mixed Nash equilibrium, simply allows for looking at a wider range of profiles than pure Nash equilibrium. Looking at correlated equilibria allows us looking at a wider range of profiles than mixed Nash equilibrium. And the condition in all the cases is the same, that nobody has the motivation to unilaterally deviate. So that's the same. However, the formalization is different. So first of all, we have inclusions only in the sense that if we identify mixed Nash equilibria with the correlated equilibria, when there is no correlation, then we have this inclusion. And in this case, and we still need to prove the inclusion because the formalism is different. So now we formally prove this intuitively clear inclusion. Given a game and a mixed Nash equilibrium, we can see this as a correlated equilibrium. So there is a correlated equilibrium such that the strategies sigma i's are distributed according to pi's. Okay, let us prove that. So the proof is as follows. We just look at the set of strategies. Now pay attention, sigma i's are the functions from the omega, from the sample space to the actual actions in S. And here let us take the sample space to be the actual actions. The probability of an action is just a multiplication of the probabilities of the mixed equilibrium. So we just assume that we directly sample a mixed, we sample an action profile according to this multiplication of probabilities. And so that's kind of an intuitive proof, but it's important to write this because again it's intuitive. But the formalization can be a bit not hard but complicated, cumbersome, I would say. And I'm trying to make it simpler than the book is. But again, you may also want to read the book, but I'm trying to make it even simpler by kind of tune it for you, by making it masticated. So for any player, now we need to define what the player's information partition is. So the for any Si and Si, for any possible action of that player in the original game, the information partition, so all the profiles, all the omegas, which are together with Si, are all the elements of S which have the same ith element. So as long as I is prescribed to the same, from I point of view, that's the same action. So we randomly get an action, but as long as I am prescribed to the same, from my point of view, it's the same sample. And now finally, the strategy of player I, given a sample, which is simply a strategy profile, is what the player should do in the strategy. So we sample a strategy profile, and then the player simply looks, what shall I do in that player, in the strategy? And that's what the player does. That's exactly what we should do. That's really the intuitive translation of mixed Nash equilibrium to correlated equilibrium. But it's nice that we are doing this because it allows kind of to feel this intuition of correlated equilibrium, which is a bit cumbersome and therefore maybe not intuitive. So this is a correlated equilibrium, first of all, because we need just to prove all the details. Why? Well, indeed, that we have this probability space, so the sum of the probabilities is indeed 1. It's simply the product probability. Now, next, all those PIs are indeed sets which constitute a division, because they definitely don't intersect. So those profiles which have the I profile SSI, they are not the same as profiles which have the I profile somewhere else. They exhaust all those possible profiles because any profile has some I profile. So any profile falls into the pi of some Si. Simply we should go to the Si, the ith element of the profile, and then the corresponding set that's it. And of course none is empty, so that's what we have here. So this is indeed the true division, right division. And SIs are indeed constant as long as the function sigma is, excuse me, I said SIs instead of sigma. Sigma is are indeed constant on those information sets, because as long as SIs are the same, then the basically sigma i's, they are projections on what I does, and as long as the projections are the same, then the projections are the same by definition. So, but everything is simple, everything is immediate, or should say straightforward. Simply the notation is a bit hard, and that's what I'm hoping to kind of guide you through. Because through the book you can probably see the same, maybe with a little bit less guidance, but it's good actually. The book allows to think a bit, and I'm trying to guide you through that because it's a bit more advanced than the basic course, so that's, I think it's nice to guide you through that. So then, the final thing to do is you need to prove that it's indeed a correlated equilibrium, in the sense that the strategy sigma is the same, is an optimal strategy given that the other players play sigma minus I, and then that the induced distribution is what we need to have, what we want to have. So why is it optimum? Why is sigma I optimum? Because the average utility, and I play sigma I against sigma minus I, why is it at least as good as playing any other sigma prime? Because playing sigma I against sigma minus I by definition is the same as simply playing the mixed strategy P, because simply those probabilities are taken from P, and playing anything else is the same as playing something else against, because the deviation is only for player I, so the deviation is indeed some Qi, and the rest play some P minus I. They just play according to this probability, which is the product probability. And from P being a mixed Nash equilibrium, which we assume, we conclude that it's at least as good to play against P minus I, to play Pi, as it's to play any other Qi. And the last thing is that sigma is indeed distributed is indeed distributed according to Pi. Why? Because C is sampled according to the product of PI's, and sigma is simply the ith element. So we first of all look at the product, and then we project it to one of the elements. So of course it's the same as just taking the element. So it's very straightforward. Just so that our definition is indeed a good generalization of what we. It's indeed a generalization. So that correlated equilibria indeed contain mixed equilibria. And now let's see that it can indeed practically model something which practically improves the situation, so that people can be motivated to play this correlated equilibria. So assume that you have two players, 1 and 2, and player 1 that's a symmetric game. So that's basically the battle of stacks. Yeah, let's revisit this and just formally say what I said already informally. So I said that by randomizing we can achieve this fairness instead of just playing a pure equilibrium, which is always unfair, because either the first player gets 2 and the second 1, or the first player gets 1 and the second 2. we can have something fair, but while avoiding those cases when we just are not coordinated, when one plays tennis and the other one plays football. And now formally, so the max-Nash equilibria are either 1, 0, 1, 0, so it's football, which gives the best possible social welfare. The total social welfare is free, but unfair, it's skewed towards player 1, or 0, 1, 0, 1, so when they play tennis, skewed towards player 2. When they play 2 thirds, 1 third, and 1 third, 2 thirds, so when symmetrically they play either that or that, but with a probability which is not 0, they play miscoordinated options, and of course they therefore lose. So the utilities are 2 and 1 in the first case, 1 and 2 in the second case, and 2 thirds and 2 thirds in the third case. So the total utility in the third case is 4 thirds, so 1 and 1 third. It's less than 3. They lose quite a lot when they play in the third case. You see, it's 4 thirds. So it's less than actually 2 even. It's less than 2. It's less than 2, and so the total utility is 1 and 1 third. It's a huge loss relatively to the total utility of 3. So how can they achieve some symmetry, some fairness, because it's a symmetric game, while having the social welfare of 3, at least something higher than 1 in 1 fourth, preferably 3? Yes, they can just do it in the following correlated equilibrium. So the correlated equilibrium is the following. You have 2 samples, whether you play football or tennis. I just could call it F and P instead of X and Y, but okay, I called it X and Y, or they called it in the book by Osborne and Rubinstein. Anyhow, you have 2 options, which represent whether coordinate on football or on tennis. And that's again a very reasonable thing that a couple, they can just say, okay, let's play randomly and decide where we go. Or just let's do it today, we go here, tomorrow we go there. But we are not talking about this repeated games here. That's why it's not something we do, but it's a similar idea. Well, randomization has this advantage of just repeating this. Not only that we don't study the repeated game here, but also that repeated game do something now and something later, and that can have different values. Because it can be that I say, yeah, I prefer getting the same thing now than a bit more later, because value can be discounted. But if you just randomize, then it's really fair. Of course, given that the randomization is fair, and indeed it's fair, so the probability of X is equal to a probability of Y is equal to half. And of course, I've made a typo, so probability of X is equal to a probability of 1 equal to half. So they equally choose between X or Y, and then both players know exactly what's going on, so both players have the finest strategy information set. And now the strategy of a player is just if any player, if it's X, then play football. If it's Y, they both play tennis. And as I said, it's practically to realize. And indeed, if you don't want to wait, of course, in the case of spouses, they can wait usually, so it will still be not exactly fair when you wait. But in the business situation, definitely you are not allowed just to say, let's do something I want today and something you want tomorrow, because tomorrow may be less valuable than today. We don't know whether tomorrow the conditions will allow doing this and so on. So tossing a coin definitely is relevant in a business setting or doing something equivalent. Okay, and now let us talk about something interesting which is inspired by the example. So this example showed something which we had those set of paths 2, 1, 1, 2, and the third. And now we have a path which is in the convex hull on this set of paths. So the new set of paths is simply 1/2. So on half of the time, you get 2, half time you get 1. So it's exactly 1/2 on average. It's in the convex hull, and the general proposition which is inspired, you may say, suggested by that, is that the paths in general, they're convex. So given a game, any convex combination of the paths of a correlated equilibria are themselves achievable as paths as the paths of some correlated equilibrium. So if you draw the paths of the correlated equilibrium on in the Euclidean space, then the convex hull is also all of those are also paths in some correlated equilibria. And by the way, the convexity can already hint you about finding them and so on, but we are not going to delve into that area, which is very wide and important and so on, and practical important. It's simply that we are not going to delve into that area in this course. So the proof of this convexity is as follows. It's quite simple. Again, it's a very nice proof to just practice your understanding of these definitions, which can be just a bit long, cumbersome. So fix any set of profiles, any finite number of profiles. So profile UI and profile UK, and look at any k coefficients in the which are non-negative and such that they sum up to 1. So that basically those coefficients they define a convex combination of those profiles. Now we need to find a single correlated equilibrium which allows us to achieve this convex combination of those profiles. Each profile is achievable as a correlated equilibrium. That's our assumption. Now we need to achieve this arbitrarily taken fixed convex combination of those profiles. So simply we are going to combine correlated equilibria. That's the intuition. Formally, for each of those k equilibria, we define for each of those k equilibria, let mu k probability k, omega k probability k, stylized p, I is the index, so I is the index, and be the C, the correct equilibrium which generates UI. So the letter, which I'm denoting this, is going to change sometimes, but it's going to always be the upper letter. So the superscript is this correct equilibrium, which path we are talking about. Now, we don't talk of generality. The spaces of those equilibria and they don't intersect. Because we are not going to use any commonality here, and so if they intersect, we can just define another space, another equilibrium, which simply has the same an isomorphic sample space. It's going to act the same way, but now this I, J, and no two spaces are going to intersect, so they're pairwise non-intersection. And now define this combination. So we define this union of all those omegas as our space. define the probability function by the following, by looking, given an element, we look in which, because it's they don't intersect omegas, there exists exactly one omega where this W is, or small omega, let's call it W. It's actually W, I think. Anyway, so there is exactly one index such that W is in this omega K. So look there, take the probability and multiply it by omega I. Now notice please that we have defined the probability space. So why? So we have a finite actually probability space. So the space is the union of finite. The sample space is the union of finite sample space. So it's finite. It's a finite union. And now the function is non-negative, and the sum is going to be the sum eventually of lambda i's, which is 1. So the sum of all those probabilities of all those w's is 1. So that's a legal finite distribution. Now define for any player. One thing, by the way, notice please that I'm talking about finite probability space. So I'm not talking about probabilities of sets, because I'm talking about probabilities of elements, and that immediately induces the probability of any sets. Any other set simply by the rule that the probability of a non-intersecting union is the sum of the probability. So because it's finite, I can just talk about the probability of the singletons, and as I said already, the probability of a singleton I just denote it to be the probability of the eminent, which is of course formally not what I mean. I mean the probability of the singleton, which consists of W. Well, okay, I hope you understand this intuitively. I'm just told you what I mean actually formally, if you want to be, because it's correct. It's formally correct. It's simply that we are for finite spaces we can write things simpler. Now define. We've defined a new probability space, which is, as you see already, a combination of the previous spaces. Defined for any player, the set of players' information set as the union of all the information sets of that player in all those correlated equilibria. So every correlated equilibrium comes with its own information set, and we are looking at the union. So I know basically player I, let's say so, player I knows, or if I'm the player I, then I know in which of those omega j's this element is, and moreover for that omega j I know in which partition information set for that omega j that is. That's what it means. And now we define the strategy as the strategy of that correlation equilibrium. So what is a strategy? A strategy takes a sample and gives us a function. Now, since omega is the union of those omega i's, we just go to the unique omega I. It's a non-intersecting union. We go to the unique omega I where this W sits. Look where the corresponding strategy of that omega sends this W and send that W there. And now, since every of those strategies is constant on the original information set, is going to be also constant on the new information set. because of the new information set. That's how they define it. This is the union. So this is all legal. And that's finally a correlated equilibrium, because it's better, because the average, let me see. That's a correlated equilibrium, and its pairs are the desired convex combination. And let us now prove why. So to prove that this is a correlated equilibrium, which is maybe intuitively true, but let us now formally prove, use the observation that a profile is a correlated equilibrium if and only for any, something we already have proven, for any element with a positive probability. What the player gets from playing the strategy, knowing that we are somewhere in the PI of that element, is that this is good as what the player gets for playing any other strategy, when the player knows that we are in this PI of this element. And since here, when we just know when I know when I'm in the PI of a certain element, I in particular know in which of the original omegas I sit. So this conditioned expectation, this already moves me to the corresponding correlated equilibrium of this omega. There I already, from the other direction of this observation, know that the required inequality holds. So basically this allows us to break the inequality, the condition, to all those information sets and that of the player, and that's how we prove the condition for every player. And that's something we can do for every player. So this is indeed a correlated equilibrium, and then the pairs of this correlated equilibrium, the expected pair, that is exactly this combination, because if we just look at the combination of what the player gets from playing the strategy against this sigma minus I of other players, when this is averaged by these probabilities, by the definition of those of omega, we can just define this to those k omegas and look at what happens for any one of them. And for any one of them, we have ui, and then we just multiply it by, which is here multiplied by lambda I. So we exactly get this convex combination of the pairs as the pair, as the expected pair of the player I in this correlated equilibrium. Well, so we have proven that for any player that holds, and so we have proven, let me just repeat, that given a game, any convex combination of pairs, any convex combination of correlated equilibrium pairs is achievable as a correlated equilibrium payoff. So as a correlated equilibrium payoff of one equilibrium. Because a convex combination means a finite convex combination. Now let us look at another example, which is also important to understand something here. And that shows that sometimes we can just look at those states and sometimes we can just ascribe a state per an outcome. So consider the following simple game. Now the pair profiles of mixed Nash equilibrium are 2, 7, 7, 2, when that corresponds to those pure equilibria, and the 4 and 2/3, 4 and 2/3, when the symmetric game has this symmetric equilibrium. Now we show, we don't even say which equilibria here, but there are those pair of profiles of those equilibria, so those two pure ones, bottom left and top right, and there is some, I don't remember, some mixed one. Now we show a correlated equilibrium, which is not pure and neither pure nor mixed, with a pair of profile outside of the convex hull of the above. And so please notice that we can have something which is outside of the convex hull of all the mixed equilibria. So it's not like the convex hull of the mixed equilibria is everything we get in correlated equilibrium. We can get something which is outside of the convex hull of the mixed equilibria. And that is the following, that's the correlated equilibrium. So the states are x, y, z, which correspond, well, we are going to say to see to what they correspond. The probability of them is 1/3 to each one of them. Player 1 knows whether we are in x or at y or z, so she can distinguish between all those two options, either x or y or z. Player 2 can distinguish between x or y or z. And the strategies are as follows. So strategies of player 1 have to be fixed on her information set. So for x it's play bottom, for y and z it has to be the same, because they are both in the same information set of player 1. Player 1 for those plays top. Player 2 for x and y, they are both in the same information set. My apologies, there is an ugly typo here. I'll now fix it. So, sigma 2 y, yes. So for x and y, which are in the same information as player 2, the player plays left, and for z, which is another information set, the player plays just play R, right? And now the strategies can be illustrated as follows. So the strategies, they basically cause us, and I again need to fix so the strategies cause us to cause the players to play the following thing. When we have x, player 1 plays B, whereas player 2 plays L, and therefore when they have x, that's what they play. When they have y, we define player 1 to play T and player 2 to play L. When they have z, player 1 will play T and player 2 will play R. Never will they play, notice, B and R, because B is only played, indeed B is only played when there is x, but when there is x, the second player plays L. So that's how they are coordinated. And first of all, notice please that this is a correct equilibrium. So we have defined those samples, probability space, that's a valid probability distribution over this finite space, those information partitions, and strategies of legal strategies, as I said, they're constant on the sets in the information partitions of the players. So that's everything legal in that sense. Now, the last requirement for a correlate equilibrium, let us what? Aha. Let us see that the strategy is optimal. So we basically check that for any concrete element, it's best to play the strategy, knowing that element for the player. So if the element is X, then one knows that 2 will play L, and therefore for one it's better to play B. So it's indeed the best reply. It's the only even best reply. But it's a best reply, that's what matters. Now if the element is somewhere in Y or Z, or Z, excuse me, the conditional probabilities of 2, because it can be that it's either Y or Z, because they are both original with probabilities 1/3, the probabilities of 2 are half for each, conditioned that it's somewhere in Y or Z. So 2 can play either left or right, this probability is half. So it's better to play T top than bottom, because if 2 plays left, it's probability half. Excuse me. Well, wait, 1 second, please. When 2 plays left, for the first player, top will give 6, bottom will give 7. When 2 plays right, the first player top will give 2, bottom will give 0. Now this multiplied by the probability, the top will give half of 6 plus half of 2, which is 3 plus 1, 4. The bottom will give half of 7 plus half of 0, which is 3.5. And therefore 4 is larger than 3.5, therefore top is the only even best response. It's the best response. And symmetrically for player 2, that's optimum, so it's a correct equilibrium. And the payoff profile is 5.5. Okay, so please notice the sum of the pairs here is 10. It's higher than the sum of the pairs in all those 3 profiles. Here it's 9, here it's 9 1/3, but it's always less than 10. Okay. The example where we could identify states with outcomes raises the question, can we always identify states with outcomes? Can we always find a correct equilibrium which realizes some distribution of outcome just having one state per outcome? And the answer is yes. So given a finite game, every distribution of the outcome, I remind you, an outcome is simply a profile which is played. So any distribution of an outcome by a correct equilibrium can be obtained also by a correct equilibrium which sample state is just a set of states of the state of strategy profiles, such that and for every person, what I know is that I know that the profiles are such that I get something. So player I knows all the sets such that their projection of I is Ti. And in the example, we also had this. So we had this set. So every outcome was a state, and player 1 could distinguish between X and Y or Z. So all those project B are X, and those who project T are Y and Z. Player 2 distinguishes between Y and X, those which project here on L, and between R, Z, and Z, which projects on R. So they can distinguish between states which correspond to their own actions. So the proof is simple. So given any a correlated equilibrium, let us define a correlated equilibrium with prime which fulfills our requirement. So we define it as follows. So omega prime, we said it should be just a set of state. The probability should be the probability of all the omegas in the original omega, such that they by sigma they are sent to play this state, which you kind of collect all the omegas which are told to play this state. Now that's a probability space, because if you sum this up, it's going to be 1, because we collect all the omegas, and of course the probability of a set is always non-negative, so the probability prime is always going to be a non-negative function. So that's a legal probability distribution of omega prime. Now we already told what we want to have as the information set. So the information sets of player I, all the sets of the form, the profiles with a projection Si for excuse me, projection Si equal to Ti for any Ti in Si. That's of course that's a division of the set of all the profiles. And the strategy of the sample, which is the strategy profile here, just sigma prime just looks at the projection of what the player I should do. And that's by definition for all the profiles which have the same projection, their projection is going to be the same. So sigma I is by definition of calligraphic P, and sigma prime is by definition constant on the partitions of player I. And the claim is that this tuple which we defined is actually a correlated equilibrium with the same outcome distribution as the original one. So as I said already, we now show that the probability primes are non-negative, and their sum is simply the sum. I have a typo here. The sum of all the omegas, also probability of omega, which is by definition 1. So the PR prime function, and I do have another typo here. There are many little details which is definitely easy to forget. So that the prime function is a legal probability distribution. Now, so that's the claim that it's, I just show you where on the slide we are. So we have built this new candidate for a correlated equilibrium. We now show, first of all, that it's a feasible candidate, and then we are going to show that it's indeed a correlated equilibrium with the required distribution. So we have showed that the PR prime is a legal probability distribution, then the set of information set is a partition of S Y, as I said, well, I didn't say this here, but I said this before. Because if you look at the different projections, so of course every profile has some projection, so that exhausts everything. The union source is everything. The intersection is empty for any couple, because if you have two sets which have different projections, they also they cannot have the same profile. And no set is empty, because for any projection there is some profiles which have this projection, so it's a feasible partition of S. So it's an exhausting non-intersecting set of non-empty sets, and sigma prime is constant on any information set, because by definition the information set is the set of all those who have the same projection, and sigma prime is the projection. So it's a feasible candidate for a correlated equilibrium. And finally, let us show why this is indeed a correlated equilibrium. So why is this optimum to play this sigma prime? So what I'm saying is that this, by the definition, you just need to show that if you just sum or all the C in omega prime of the probability of prime of C times the utility, if you just sum this average expected, the expected utility of what plane I have when playing sigma I prime against sigma minus I prime, it's at least as good as play I would get an expectation if she deviates to any tau prime instead of sigma. Please notice that here the original correlated equilibrium is omega. The new one we're going to prove it's a correlated equilibrium is primes. And prime here is not a deviation, it's simply the new correlated equilibrium. The deviation here is denoted by tau instead of sigma. So prime here is the new, and the deviation is tau instead of sigma. Now this happens if and only if now we just we just by definition of probability we just go over all the excuse me, yeah, so omega prime is set of strategies. You can just go, it's the same as go in over all the elements in omega prime. It's the same as going over all the strategy profiles. Now, the probability is the same as the probabilities of the set all the omega who ascend to S by the definition of the probability of PR prime. Now, what the last translation we need to do is look in what is Si prime. That's the ith component of this profile. So we just eventually, when everyone plays again according to his or her Si prime, we just have S as an entity. And that should be at least as good as the same thing as when play I allows some deviation to T I prime. And now that is exactly the same as going over all the omegas. Instead of going over s's and looking at the omegas which are sent to s, we can go over all the omegas and just use those s's where omegas are sent and use the probability of omegas. And the last condition is already the condition we have from the assumption that omega PR, calligraphic P, and sigma s is a correlated equilibrium. So we have managed to show that the new profile is optimum if and only if is the best response, if and only if the original one is the best response in its own probabilistic structure. So we proved that this is a probability, correlated equilibrium, and now we need to prove that the distribution of outcomes is the same, but that's something which we of course see from the construction. So the outcomes the probability of an outcome S is the same as its probability by definition of PR prime in the originals in the original correlated equilibrium. So we've proven that we can basically confine our attention to correlated equilibria which just have a state per strategy profile, and where the person, the player, knows what is her action in this state. So basically, we just say, okay, we just basically have come back to the original motivation. So we say that we can just randomize or which profile we play. You don't know which profile the others have to play. You have to just know that the randomization has decided that you should play this one, and then it's best for you to play this one. Okay, now we're finally done with correlated equilibria, and now we are moving to the next notion, which is case-strong equilibria.